Have you ever wondered how many times you would have to flip a coin until you finally see heads? Or how many job interviews a candidate must attend before receiving their first offer? This is not just luck, it is mathematics. Today, we dive into the geometric distribution, the probability model that counts the number of trials needed to achieve the first success in a series of independent events. To understand the geometric distribution, we must first talk about its foundation, the Bernoulli trial. Imagine a single event with only two possible outcomes: success with probability p and failure with probability q, which is simply 1 minus p. For the distribution to be geometric, each trial must be independent. The result of the first flip doesn't change the odds of the second. The formula for the geometric distribution is elegant and intuitive. Let x be the random variable representing the trial number of the first success. The probability that the first success occurs on trial t is p of x equals k equals q raised to the power of k minus 1 multiplied by p. This means we had k minus 1 consecutive failures followed immediately by one success. Let's visualize this. If the probability of success is 20%, the most likely outcome is succeeding on the very first try. As we move to the second, third, and fourth trials, the probability decreases. This creates a decaying shape. Statistically, the expected value, or mean, of this distribution is 1 divided by p. If your success rate is 10%, you should expect to succeed, on average, by the 10th attempt. One of the most fascinating and counterintuitive properties of the geometric distribution is that it is memoryless. Suppose you are playing a game with a 1 in 50 chance of winning. If you have already played 49 times and lost every time, the probability of winning on the 50th try is still exactly 1 in 50. The universe doesn't remember your past failures. Your probability of needing n more trials is independent of how many you've already attempted. In the real world, this distribution is everywhere. In quality control, engineers use it to determine how many items must be inspected before finding a defect. In cybersecurity, it models how many brute force attempts a hacker might need to crack a password. In biology, it can model the number of DNA base pairs until a specific mutation occurs. It is the math of persistence and the statistics of the first time. In summary, the geometric distribution helps us quantify the weight for success. Whether in sports, business, or science, understanding the k-1 failures allows us to manage expectations and resources. Remember, the mean is 1 over p, the shape is always decreasing, and the trials are independent. References: Ross, Sheldon M., Introduction to Probability Models; John E. Friend, Mathematical Statistics; Gujarati, Damodar, Basic Econometrics; Feller, William, An Introduction to Probability Theory and Its Applications.